Pleasure to introduce Johnathan Rudd. Johnathan got his BSc from Queen's University in Geological Engineering, Geophysics, and he worked for various ground consulting firms for 5 years, but then he moved into airborne, where most of his career has been in various airborne companies, Dijem, Fugaro, AeroQuest. Then more recently, he's moved into distributed array DCIP technology with Quantech. And just recently he's joined Discovery Geophysics, and we've spun off a new company called Geophysical, which Johnathan's going to be a part owner and president. DIAS, spelled D-I-A-S, DIAS Geophysical, which is a new 3D DCIP technique. He won't be talking about that today, however. You have to stay tuned for that. What he will be talking about is another initiative that we're doing with GAP Geophysics, with their SAM technology, and he's going to be talking on the results of a HeliSAM survey over the Lalor deposit. His co-authors are Chris Parker with GAP Geophysics, Mel Catach, who's here from GAP Geophysics, and Johnathan Kuttai with Discovery.
Good morning, and thanks, Dennis. I'm going to skip that front page as you've already done.
Sorry.
Covered all that stuff. That's great. So today I'll be giving a bit of background to this test survey. It was done quite recently. Give a little bit of information on the Lalor deposit. We've had a lot of that already. And then get into describing the SAM technology in general, and then more specifically the HeliSAM implementation of SAM, and then take a look at the survey results, and then make some conclusions about it. So the test survey was flown as a collaboration between GAP Geophysics Australia and Discovery International. The survey was done in August, so as I mentioned, quite recently, and it followed a commercial HeliSAM project that was completed in Alberta in August as well. And as a preview, HeliSAM produces a useful result over the Lalor deposit through the use of an inductive ground loop source, using sub-audio frequency excitation and a total field airborne magnetic receiver. So not to belabor this, we've seen a lot of this information, but probably worth mentioning that the discovery by the Hudbay team was really brownfields exploration. It used a Crone large loop EM system through the use of multi-turn transmitter loops and long stack times. Again, lots of information we've heard about here, but I think the points that I'd like to bring across here are that it's a large deposit. 30 million tons is a very large target, and which makes it feasible to detect from surface. But also details about the alteration and mineralization. Through the analysis of this data set, we're convinced that we're seeing all three zones, the zinc-rich and certainly the zinc-rich, in the relative near surface, the copper-gold rich, which is the deeper portion of the deposit, and possibly the middle zone as well, the gold-rich zone. And the reason we're probably seeing that is the prevalence of pyrrhotite, which net textures very rapidly as a matrix in that mineralization. So the sub-audio magnetic technique is a proprietary method. It's developed by GAP Geophysics, primarily Mal Catach. It's a mature technology, been in commercial operation for more than 10 years now. The method produces both electrical and magnetic characteristics from the data. And its applicability in a wide variety of application is driven by a number of different surveying modes, and I'll describe a couple of them here. We see some data examples, total field magnetic on the left top, magnetometric IP on the bottom left, and magnetometric resistivity on the bottom right. So I mentioned modes. We have two basic transmitter modes for the SAM technique. The first is an inductive loop mode, so you put out a large loop. Could be one loop or two loop, usually one, and then you transmit through that. The second mode is a galvanic mode, where you're injecting, you put out 2 electrodes and you inject your current directly into the ground. And then the survey areas in the middle of those 2 electrodes. And in practice, those electrodes can be quite small for a small-scale survey like UXO, or it can be very large in the order of 10 to 20 kilometers apart in some applications. The SAM receiver is developed by Gap Geophysics, called the TM7 receiver. It samples up to 10 kilohertz and can be used in a variety of modes, ranging from a stationary mode, which is what the Samson technique is called, to a walking mode, which you see in the picture on the bottom. It can be vehicle mounted, or it can be airborne. And the airborne mode is what we'll be showing you the results from today over Lalor, the HeliSAM. The data that we get off the system is processed for a variety of parameters, as mentioned. One that I don't show here is the total field magnetic measurement. That comes out obviously because it's a total field magnetometer. But from the data set, we're able to derive total field magnetometric resistivity, EM data, and magnetometric IP as well, through the various portions of the waveform. The HeliSAM system, so this is the HeliSAM mode of SAM, is characterized by a large induction loop. You can also use helicopter receivers over the galvanic, but here we'll talk about induction loop. In this case, we used a Phoenix TXU transmitter. The waveform, 50% duty, transmitting at anywhere from 1 to 10 hertz for the HeliSAM mode, and a sample rate up to 10 kilohertz, as mentioned. Positioning is very accurate using real-time differential GPS in the bird, where the mag sensor is, and the sensor height is normally 40 meters above ground level. And again, the laser altimeter records that in the bird for accuracy. And then we use a base station reference for the processing of the data. So in this case, in this example, we've used a TXU-30, but Gap, their subsidiary Gap Geopac, produces high-power transmitters, 70 kilowatt, 80 kilowatt transmitters called the HPTX-70, and then they have another one for IP application, IPTX-2500. So what are some general characteristics of HeliSAM? Operationally, it's a towed bird system, so it's really very easy to implement, plug and play. It's airborne acquisition, so you don't have to cut lines for your receiver acquisition. And of course, in a helicopter, it's a very rapid acquisition. On the data side, because it's a towed bird, you don't have any aircraft corrections to make to the data. You can contour really any terrain, and you get uniform data resolution. It is full waveform data acquisition, and you can process the data. It's not, as high volume perhaps as some other surveys, so you can rapidly process that data in the field. But the 3 main points I'd say, or maybe the most important points, are the low noise characteristics of this total field measurement. We've put a similar graph up here in the top right of B field sensors, and this total field magnetometer sits in the SAM TM7 magnetometer sits somewhere in here in terms of its noise characteristics in that sub-audio frequency range. So very low noise and forgiving because you're not measuring components. B field measurement is the other important factor, and then the ability to transmit a low base frequency and select that base frequency as appropriate for the application. So more specific survey details of the test survey. We used a pre-existing single loop transmit loop, about 1.7 by 1.7. As I mentioned, the TXU-30. It was a 13 kilowatt generator, so we didn't use all of the capacity of the transmitter. We operated the survey at a 7.5 hertz base frequency and achieved a 20 amp peak current in the transmit loop, which produced a peak dipole moment of 57 million ammeter squared. The helicopter, it's a light system, so we used an R44, relatively inexpensive and readily available. And the total installation time is about 5 hours and 4 hours of flight. That includes some training, some frequency test flights. The survey itself only took a couple hours. And the average survey speed was just under 100 kilometers per hour. HeliSAM survey plan, so you can see here the lines were flown at 100-meter line spacing, a total of just under 100 line kilometers. We did fly the whole block shown here. The 3 lines of interest are 5350, 5600, 5850. There seems to be different line numberings in the various surveys we're seeing here today, so you might want to take note of where those lines occur relative to the infrastructure and the deposit. So we'll get to the results. The first image here is of the total field magnetic data. So the resolution that you'd expect out of a low-flying helicopter mag survey, offering lots of detail. You can see that the flight path took the sensor around the actual mine site, so we don't have coverage in that area, and that's consistent for the other data sets as well. Getting on to the EM, there were 16 channels of EM data. We took each channel and gridded them up in plan view and then colored it accordingly. So we run from about 0.4 milliseconds in the first channel to 25 or so milliseconds in the last channel. So I'm just going to step through channel 1 through 16 here and let you see that. This, just for reference, this outline is a outline that I got which represents the full extent of the Lalor deposit, including the down dip disseminated portion. So that's the 1.4 kilometer by 600 kilometer wide total zone. And because I never catch everything the first time, I'm just going to run through that again. So you can see there's 2 fairly distinct lobes in this response in the late time, one over that lower disseminated zone and one over the zinc-rich upper zone. Quite an interesting response. So we're going to take a look at some of the profiles, and these again are the profiles that I mentioned across these common lines, I guess, from other surveys. I'm going to go from the southeast to the northwest, so the last one will be the one that goes across the mine site. So the first profile here shows a very clear response. Some cultural noise off to the east here, a small power line that runs towards the back edge of the survey. And the last line. And as I mentioned, you can see some cultural effects due to the mine site on that southern flank of the response. These are just channels 8 through 16, so the later channels. So the noise level, if you kind of look at this, is about 0.1 picoteslas per amp. Obviously the early time response, taking a look at some of these images, the early time response is contaminated by that power line, which extends right along that road. It's obviously coupling very well to the system, and we can confirm that obviously by taking the data, doing a notch, and we see all of the 60 hertz sources in the area. You can see there's another road that runs up through here, which has some cultural noise as well. So this is the last late channel response. We're obviously going to want to model this. We did some modeling with EMIT's Maxwell software, and we tried modeling it with one plate. Did not receive a particularly pleasing fit, so we added a second plate, and the bottom result there is the fit that we were happy with in terms of a two-plate model. And those plates you can see here with reference to the known mineralized meshes. Here the green one is the upper plate, which tops out at around 600 meters, and then the lower plate, which extends down at a steeper angle to well below 1 kilometer. So, well, lots of response, fairly low noise levels relative to the signal. Let's see what happens as we drop this model to depth. How will HeliSAM be able to detect it at deeper depths? So we did this for the existing loop and transmitter. So the 57 million ammeter squared power source. That's the original model result. And then as we go to depth, we drop it down 200 meters. Your last channel is still at 6 times the noise floor. Drop it down 400 meters, and you're still at 4 times the noise floor in the last channel. Drop it down to 600 meters. You're still 2 times the noise floor in the last channel. So there's still room there, and you would get a reasonable characterization of a source at a little over 1 kilometer depth for this size of a target. So what happens if, as Sid mentioned, you use a bigger hammer? As I mentioned, GAP does make these high-powered transmitters. Have a chat with Mal. They're incredible units. They lots of safety provisions in them, and they output a 70 kilowatt power at 1200 volts. So if you put one of those units onto a 3.3 kilometer loop, you'd be able to achieve about 50 amps in your loop, which is approaching 500 million NIA, which is a big number. And that power, coupled with that model that we developed from the real data, would produce a response like the top right image there. And then if we take that model and drop it down, we can see that at 400 meters deeper, you're still well above noise. 600 meters, 800 meters, and at 1 kilometer deeper, you're still going to be able to detect this thing. These are channels 11 to 16. So then we took a look at we take a look at what's, this loop is ideally coupled. In a real exploration environment, your source might not be directly under the loop perfectly coupled. So we moved our source off to the side so that it's kind of under the edge of the loop. And we can see that we're going to get a response which is about twice noise in the last channel. So again, fairly easily detected with this is the 57 million ammeter squared system. And comparing that to the perfectly coupled or the designed coupled system response. So what are the key factors in the success of HeliSAM in this particular application? I think clearly the signal level is. We compare 1 million ammeter system, which is maybe fairly typical of helicopter-borne systems. The power of the transmitter looks like that. At the 750 meter depth, which is kind of the middle of that upper loop, your field strength is 0.4 nanotesla, and with these larger, with a larger ground loop, you're looking at a field strength of 16 nanotesla at that 750 meter depth, so about 40 times the power. So that's the main factor. Sorry. The other factors are the fact that you're able to deliver a low base frequency. and measure with the B field instrument. And then there's obviously the survey efficiency of an airborne receiver system. So how would we envision a brownfield exploration program for massive sulfide, whether it's VMS or nickel? We would look at contiguous transmit loops, perhaps 2 by 2 kilometers or 3 by 3 kilometers, using a common side, and then just marching along a zone of interest. A high power transmitter would be the preferred mode, obviously to maximize signal to get as deep as you can. And then we would likely increase the sensor height a little bit, provides several benefits, enhances your safety in operation, gives you a little bit more flexibility in selecting your frequency, less cultural and surface noise if it's an active area, and probably a fairly small penalty on survey sensitivity because you're really looking at deeper sources in this type of application. So in conclusion, HeliSAM's demonstrated a good ability to detect and provide characterization of this deposit in a relatively low power implementation. It's a rapid exploration method, which has implications for project cycle times and coverage, ability to cover larger areas in a season. It's a cost-effective tool for deep exploration, even in challenging environments. And it's sensitive to highly conductive sources because of the B field receiver and the low base frequency. And it does yield multiple parameter data sets for better characterization of the survey area. I'd like to acknowledge BC Geophysical Society and GAP Geophysics, Hud Bay, and Discovery as well. Thank you very much.
Well, of course, I'm a little bit biased here, but I'd say that's a very nice piece of work. Could we have some questions, please, from anybody?
Yes.
Ken.
Ken.
Anybody who does a hybrid system is very brave. The last one I remember was Turair, and it didn't work out so well. But the question, it kind of, I guess, it begs the question: did you run the thing with your transmitter off to see what the bloody power line was doing from the point of view of the signal? So you're talking brownfields, you're talking places that always have power lines. So why not just look at the existing field off of that? It looks like it's pretty well coupled to the target. And the second part would be when you get these very large currents going through wires in the ground, and certainly coming out of Australia, they're aware of the regulations now that affect IP. People are requiring their, like when you've got a pole dipole, right, I understand, put power lines up to actually get those wires off the ground. And I don't think Canada's totally immune from that. So sort of maybe comment about that if you could, for the first part, maybe yes or no. Was it run without the transmitter?
No, I don't believe it was. Glenn Chubik was there at the survey. He's shaking his head. No, it wasn't. It's a great idea. It would alleviate some of your loop laying concerns that you mentioned in the second part there. And yeah, loop laying is always a concern, and Discovery's quite experienced in that, and various jurisdictions have their different requirements for that. So it's just part of doing ground geophysics.
Yeah, sure. I had a quick question. With the total field sensor, is there a way to get all three components out of that?
Yeah, sorry, I should have mentioned that, Peter. You're right. There is a way to derive your three components. It's a well-trodden path. This data set, we are working on that, I guess, Mel. Is that right? Haven't had success. There's some complications when you have a noisy environment because of the high-frequency content in the data. So there's some challenges in that. But yes, we would normally get a three-component data set out of this, and you could model the three components. But in this application, the total field is quite sufficient for the purpose.
Question here in the, go ahead.
What's that generator weight, that large one?
Yeah, the HP70 is a 2-ton, so you'd have to bring it in with a truck, so the access is an issue. The the high power IP transmitter is modularized, so it would be much more easy to get it into difficult environments. Mal, did you want to comment any further on
Yeah,
that?
Mel, stand up so everybody can recognize you.
Sorry, what size of generator?
An A-star helicopter, I'm just trying to think, what you can do
Yeah, so Mal, could an A-star pick up your high-power IP transmitter? $500 kilograms? Yeah, and that. And yeah. Right. Well, the trade-offs are stacking time as you're flying across, of course, versus the benefits of having the lower frequency. Mal, did you want to comment on the frequency range? I think we state 1 to 10, but more practically maybe 4 to 8 would be more typical.
Okay, I think that's good. Thanks a lot. Here's your salmon.